This is a demonstration of the 555 integrated circuit in its astable, packed form, being used to generate a continuous clock signal. The output is displayed visually on an LED connected to the 555's output. The frequency of the square wave signal is determined by a resistor and a capacitor in the timing network. In this setup, the capacitor charges through R1 and a potentiometer, acting as R2, allowing the frequency to be adjusted. As the capacitor charges and discharges, the voltage rises and falls between 1/3 and 2/3 of the supply voltage, triggering the internal comparators and flipping the internal SR latch. This process repeats continuously, producing a stable square wave output, which can be observed on the LED. Next, in the unpacked 555 version, the same functionality is recreated using discrete components: an LM358P dual op-amp, a CD4001 NOR gate SR latch, and a CD4069 inverter. The LM358P comparators monitor the capacitor voltage, comparing it to the 1/3 and 2/3 supply references provided by a resistor voltage divider. When the capacitor exceeds these thresholds, the comparators trigger the SR latch, storing the output state. The CD4069 inverter buffers the signal, providing enough current to drive an LED and an NPN transistor that controls the capacitor's charge and discharge cycle. This unpacked setup demonstrates the internal workings of the 555, showing how voltage dividers, comparators, and the latch interact to create a square wave signal. Finally, the square wave output from the 555 is used to drive a CD4510 4-bit BCD counter. Each rising edge on the clock signal adds to the counter, with its 4 outputs connected to the LEDs to display the binary value. Q1 is the least significant bit, on the right, while Q4 is the most significant bit, on the left. As the 555 pulses, the LEDs change to represent the count from 0 to 15 in binary, repeating continuously. The frequency of counting can be adjusted with the potentiometer in the 555 timing network, changing how fast the LEDs cycle through the binary sequence. This application shows how the 555 can generate clock signals for digital circuits, providing a clear example of binary counting.